Okay, so this unit covers reaction rates and equilibrium, and this is another shorter unit, so we should be able to get through this PowerPoint fairly quickly, and you should be able to complete this unit fairly quickly. So we're going to begin with reaction rates. We really are splitting this unit into two separate sections. Reaction rates and equilibrium are related to one another, but they're really two different topics. And if we were able to study them in more detail, each one would be a separate unit. But we don't have as much time as I would like, so we're just going to kind of run through the basics of each. So kinetics is defined as the study of reaction rates. And a rate is just how fast something is going. So we're going to look at some reactions and we're going to see what controls how fast that reaction goes. And the whole study of kinetics is based on the idea that particles are in constant motion. Now, why is the study of kinetics important? Well, if you were studying this as a career, it's used to determine the reaction pathway, which is also known as the mechanism of a reaction. And if you know the way a reaction takes place, then you can do things to that pathway to modify that reaction. For instance, if there's a chemical reaction in your body that produces something that is not desirable, then if you know that mechanism, it's possible to maybe alter that mechanism with a better outcome. So we're going to first look at kinetics. So the main idea behind kinetics is that particles, like I said, that are in constant motion have to collide in order to react. So in general, the more collisions that you have, the faster the reaction is going to go. Now, the problem is that not all of the collisions, not every time that particles collide does it result in a reaction. So we're going to look at next what makes an effective collision. So an effective collision is one that results in a chemical reaction. So if you look at this reaction right here, we have NO, which is nitrogen monoxide, reacting with O3, which is ozone. And the products are supposed to be NO2 and O2. Now notice these first two reactions, the products are NO and O3, which are the same as the reactants. So that would be considered an ineffective collision. In this last example, we have the desired products being formed, so that's an effective collision. So we're going to look at that in some more detail. Not this particular reaction, but another reaction, and we're going to look at the factors that control whether or not a collision is effective. So there are two main factors that control whether or not a collision is effective. And those factors are activation energy and orientation. So we're going to look at each of those separately, and we're going to see how they control a reaction. So the first thing I want to mention is something called a transition state. All right, so this is a reaction that we're going to look at. We have CO plus NO2 yielding CO2 and NO. That's our reaction. So basically, if we look at what's going on, these are the two reactants. We have CO and we have NO2. So here's CO and here is NO2. Now the bond between nitrogen and one of the oxygens must break. So this bond right here is going to have to break. That oxygen then is going to have to form a bond. I don't really want to erase. Is going to have to form a bond then between itself and the carbon. So this bond is going to break, and then this bond is going to form. Now you're going to get a species that's going to be in between those two. And that species is called the intermediate. So when the intermediate forms, there's going to be a part of a bond here and part of a bond here. So this bond is breaking and this bond is forming. So I just wanted to kind of let you know or give you an idea of what we mean when we say transition state. All right, so let's get to the next slide. All right, so again, we're going to look at two factors that control whether or not a collision is considered effective. And the first one is called activation energy. Now, activation energy is defined as the minimum energy colliding particles must have in order to react. So it's also known as the startup energy. And to give you a practical example, let's say you were going to start a bakery. You wanted to open your own bakery. So what you would do is you would have to find a storefront. You would have to purchase all of the equipment that you need. You would have to buy the ingredients. And so you would have to spend some money, some startup money, before you could start making money. So that's kind of what a activation energy is for a reaction. It's the startup cost for that reaction. So let's look at an energy diagram. So we have the reactants here, and then on this side we have the products. So we've got reactants and products. So the activation energy is the amount of energy that's necessary to get from the reactants to that transition state. Remember, we said the transition state is that that species that exists between the reactants and products as bonds are being broken and new bonds are being formed. So activation energy is always the distance between the reactants and the transition state. Now, another way of looking at this, another practical example, let's say you were going sledding and this was the hill. Okay, in order to go down the hill, you need to push your sled to the top of the hill. So it's going to take some energy for you to get your sled to the top of the hill, and then you can move down freely. So that is an example, again, of activation energy. Now, activation energy exists whether or not a reaction is exo or endothermic. So if you look at these two reactions, reaction A is exothermic. And I'm just going to write exo. How do I know reaction A is exothermic? Because the products have less energy than the reactants. So the reaction is giving off energy, generally as heat. And so the activation energy, though, is still the distance from the reactants to the top of that energy peak. Now, this is still an exothermic reaction. Again, we have activation energy. This is just a reaction that takes more activation energy. I will try to find and insert a diagram of a endothermic reaction, but the same thing would happen in an endothermic reaction where the reactants have less energy than the products. So if I wanted to sketch an endothermic reaction, here would be the reactants, here would be the products, and then the diagram would look something like that. So in that case, again, activation energy still exists, and it would be the distance between the, again, the reactants and the transition state. So here's the reactants, and here are the products. So this is an example of an endothermic reaction, where the products have more energy than the reactants, meaning that the reaction must have taken in energy as heat. Okay, so again, the activation energy can vary for different reactions. It really doesn't, you know, there's no trend or no way to actually predict it. You just, it's calculated experimentally for different reactions. We're not going to get into that right now. All right, so let's move on. The other factor that must be met is that the reactants must collide with the proper orientation. So this is the reaction that I wrote down earlier. So if we look at that reaction, and if you remember what I wrote down earlier, we said that in order for this reaction to take place, there was a new bond that needed to form between carbon and one of the oxygens from NO2. All right, so that was N. So again, the bond between nitrogen and oxygen had to break. So this bond had to break, and this bond needs to form. So that means that these two particles or these two molecules have to collide in such a way that the oxygen is facing the carbon. So the oxygen of NO2 has to collide with the carbon. So if you look at this bottom collision, we have the black molecule is the oxygen, and is the carbon, and the red is the oxygen. So here the nitrogen is colliding with the carbon. Well, nitrogen and carbon don't want to form a bond, so that's an ineffective collision. In this bottom diagram, now you have oxygen colliding with carbon, and so this bond can break and they can form a bond right here. So you can see the new bond was formed and the bond here was broken. So those are the two particles that must, or the two criteria that must be met for an effective collision. It has to combine with enough energy to overcome activation energy, and it also the particles must have the proper orientation. Now, there are some things that you can do to increase or decrease the rate of a chemical reaction. And again, these things will either help to improve the orientation, help to improve the energy, or just give you more collisions. Because again, the more collisions that you have, the more likely that you're going to have ones that are effective. So, one factor that affects reaction rates is the temperature. And in general, increasing the temperature will increase the reaction rate. Now, why is that? Because at a higher temperature, the particles are moving around faster. They have more energy. So they're going to collide more, and they're going to collide with more energy. The second factor that will affect reaction rate is concentration. So if you increase the concentration, generally that will increase the reaction rate. And again, these are generalizations. There are reactions that don't apply to this, but in general, increasing the concentration increases the reaction rate. And why is that true? Well, because if you have more particles, they're more than likely to collide. And more particles means more collisions. Now, the third factor is adding a catalyst. So a catalyst is defined as a substance that changes the rate of a reaction without being changed itself. So you put the catalyst in the reaction, the catalyst comes out of the reaction unchanged. So how does a catalyst work? Well, it provides an alternate pathway that has a lower activation energy. So if you look on this diagram, okay, so this is the activation energy of the reaction, the distance from here to here. When you add a catalyst, again, which provides a new pathway, you have this activation energy then. So you have this new, the transition state has less energy, and it lowers the amount of energy needed to react. Now, how does it do that? Again, it usually provides a different pathway for the reaction to take place. All right, so let's take a look at the first in-class exercise. In this unit, I've included the in-class exercises with the PowerPoint itself. So the first in-class exercise says, a quart of milk spoils quickly if left at room temperature, but keeps for several days in a refrigerator. Explain. Right, so let's go back and look at the factors that affect reaction rates. The first one was temperature. We said that when you increase the temperature, it increases the reaction rate. So milk spoiling is a chemical reaction. Bacteria in the milk will make it spoil by reacting with things in the milk and producing byproducts that are not desirable. So if you put the milk in the refrigerator, you've lowered the temperature. Lowering the temperature then will slow down that reaction rate. So lowering the temperature decreases the rate of the reaction. All right, so that's all that we're going to say on reaction rates. Now we are going to start looking at equilibrium. So equilibrium is important because in the next unit, when we study acids and bases, it's really just an application of equilibrium. So equilibrium is a condition or a state where the rate of the forward reaction is equal to the rate of the reverse reaction. And so in equilibrium, we are going to be looking at reactions being reversible. So I've gone back through and I've added another slide, which is, I forgot to add it the first when I was making up this PowerPoint. And that is the fact that many reactions are what we would consider reversible. So we've been used to looking at reactions going in one direction, where the reactants, in this case SO2 and O2, go to form products. But in real life, as SO3 is being formed, it can collide, SO3 particles can collide with one another and break back up into SO2 and O2. So whenever you see this double arrow, that means that the reaction is reversible. Excuse me. So then equilibrium is the condition where that forward rate is equal to the reverse rate. So if you look at what happens, I'm going to go back to our reaction. When the reaction first starts, you only have SO2 and O2. So if you look at the rate of the forward reaction, it's going to start out, at a certain point, and then as it proceeds, it's going to, and I'm not tracing this very well, but it's going to slow down. So let's erase that. The reverse rate then is going to start out essentially at 0, because when you first start a reaction, you don't have any products. And then that rate is going to increase till it gets to a certain point. And eventually you're going to get to a place where the rate of the forward reaction is equal to the rate of the reverse reaction. Once you reach that point, you have reached equilibrium. So equilibrium is a condition. It's the place where the rate of the forward reaction is equal to the rate of the reverse reaction. It's really important, though, to remember that you still have motion going in both directions. Now, at the macroscopic level, on the big level, it's going to look like nothing's happening because the rates are equal. But on the microscopic level, products are still being formed. They're just being formed at the same rate that reactants are being reformed. So we say that equilibrium is a dynamic condition, meaning motion is still taking place. So we are going to look then at what's called an equilibrium position. Now, the equilibrium position is just the concentration of reactants and products at equilibrium. Now, some reaction will, some rates will become equal when you have equal amounts of reactants and products. Some rates will become equal when you have a lot more products. Some rates will become equal when you have more reactants. So we're looking at reactions in a different way now. We've always looked at them as these are the reactants. They completely react and form products, but that is not always true. Some reactions don't form a lot of products for a variety of reasons. And then once we get those concentrations, we're going to calculate what's called an equilibrium constant, which is known as K or KEQ. So whenever you see K in a book, or K and KEQ mean the same thing. Capital K always stands for the equilibrium constant. And the equilibrium constant is just the ratio of product concentrations to reactant concentrations at equilibrium. So we're going to look at this in a little bit more detail. So this is a generic reaction. So in this generic reaction, we have A moles of substance A plus B moles of substance B is in equilibrium with C moles of substance C divided by D moles of substance D. So the equilibrium expression is the concentrations of the products over the concentrations of the reactants raised to their coefficients. So when you see those brackets, not writing very well, sorry. Those brackets, when you see them written like that, they stand for concentration. And by concentration, we mean molarity. All right, so those brackets stand for concentration. So it's the concentration of substance C raised to the number of moles of substance C times the concentration of substance D raised to the number of moles of substance D divided by the concentration of substance A raised to the number of moles of substance A times the concentration of substance B raised to the number of moles of substance B. Now, a few important things to remember. These are not additions or subtraction. This is multiplication. So it's the concentration of C raised to its moles times the concentration of D. And same with A and B. And it's products over reactants. Now, the other thing is that equilibrium, when we're looking at things at equilibrium, we only pay attention to substances that are either aqueous or gases. Liquids and solids are not included in the equilibrium expression. Okay, so let's go through and do a couple of examples. I want to now do in-class exercise number 2. And we're going to write the equilibrium expression for several reactions. There's actually 5 of them. And hopefully, I mean, this is not usually something that people find very difficult. So let's look at the first reaction. So we have 2H2O2 is in equilibrium. That's what this double arrow means, with 2H2O plus O2. So H2O is hydrogen peroxide. It forms an equilibrium with water and oxygen. So our equilibrium expression is the concentrations of the products raised to their coefficients divided by the concentration of the reactants. So the first product is H2O. So we have the concentration of H2O. Now H2O has the 2 there, so we're going to square that. The second reactant or product is O2. So times the concentration of O2. Now the coefficient of O2 is 1. There's 1 mole of O2, so you don't need to write the 1. Divided by the concentration of H2O2. And then again, this 2 means that it's going to be squared. So that's all there is to writing an equilibrium expression. So let's do the rest of the examples. Okay, the second one is 2NH3, which is ammonia, is in equilibrium with N2 plus 3H2. So again, it's products over reactants. So the first product is N2. So it's going to be the concentration of N2 times the concentration of H2 raised to the 3rd power divided by the concentration of NH3 squared. Right, so let's look at the third example. So we have SO3 plus water yields H2SO4. So again, we said that in an equilibrium expression, we only include things that are gases or aqueous. We do not include things that are liquid. So what that means is that water is going to be left out of the equilibrium expression. So the equilibrium expression is going to be the concentration of H2SO4 divided by the concentration of SO3. So again, when something is a pure liquid or solid, you leave it out of the equilibrium expression. All right, so there's 2 more in-class exercises, and I would urge you to pause the video and do them yourself and then check the answers. So when you do this first one, it's again products over reactants, so it's the concentration of HI raised to the 2nd power because the coefficient of HI is 2 divided by the concentration of H2 times the concentration of I2. And then the last one, which is E, and it's not labeled E on here, I apologize. But you have, again, a solid and a liquid in here, so those are left out. So the equilibrium expression is just going to be the concentration of oxygen raised to the 6th power divided by the concentration of CO2 also raised to the 6th power. Okay, so next what we're going to do is put some numbers into the equilibrium expression, and we're going to get a value for K. And when you get a value for K, if K is greater than 1, because again, equilibrium is products over reactants. So products are on the top of the fraction and reactants are on the bottom. So if K is greater than 1, that means the number on the top was bigger. And so we say the products are favored. If K is less than 1, it means the reactants are favored. So let's do the next couple of in-class exercises which will illustrate this. So this is in-class exercise number 3. It says the following reaction was allowed to reach equilibrium at 25 degrees Celsius. Under each component is its equilibrium concentration. Calculate the equilibrium constant for this reaction. Does it favor reactants or products? So these blue numbers are the concentrations. So the concentration of NaCl at equilibrium was 2.6. The concentration of NO is 1.4. The concentration of Cl2 is 0.34. So the first thing you want to do is write the equilibrium expression. Oh, and it's not going to let me click on it without getting rid of the pen. Okay, so the equilibrium expression, let me go back, is going to be the concentration of NO squared times the concentration of Cl2, and I just wrote them in reverse order, but it really doesn't matter, divided by the concentration of NaCl squared. So when you put your numbers in, the concentration of NO was 1.4. So I put 1.4, and that is squared. The concentration of Cl2 is 0.34. So I put 0.34, and that doesn't have any coefficient, so I'm not going to do anything to that. And then the concentration of NaCl is 2.6. And again, I want to square that. Now, probably the biggest mistake that students make is when they do the math, they don't square it. Or do the squares. So make sure that you do the squares. Also, you want to really show as much work as possible, because let's say you wrote the equilibrium expression correctly, but then you forgot to square it, you would still get partial credit. So when you do the math, you get a value of 0.099. Now 0.099 is a small number. It's definitely less than 1. So we would say in this reaction that it favors the reactants, because again, it's products over reactants. So at equilibrium, the amount of reactants, this number on the bottom, was bigger than the number on the top. So once this reaction reaches equilibrium, you're going to have more NaCl than you will NO or Cl2. So let's look at the next in-class exercise. It says, what is the equilibrium constant for the following reaction? Equilibrium concentrations are given under the formula of each component. And again, does the reaction favor reactants or products? Okay, so the coefficients of everything is 1. We have 1 mole of PCl3 plus 1 mole of Cl2 yields 1 mole of PCl5. So the equilibrium expression is going to be the concentration of PCl5 divided by PCl3 times Cl2. Remember, it's always products over reactants. So 1.66 was the concentration of PCl5, and then 0.83 was the concentration of both PCl3 and Cl2. So you get an equilibrium of 2.41. 2.41 is greater than 1, so we say that this favors the products. That means the number on the top was bigger than the number on the bottom. So at equilibrium, you had more products than you did reactants. All right, so the last thing that we're going to look at in this unit is what happens to a system at equilibrium when you apply stress to that system. And that's defined or described by Le Chatelier's principle, which we will be doing a lab on. So the next lab that you will do, or that we'll do together, is a Le Chatelier's principle lab. So Le Chatelier's principle says that if stress is applied to a system at equilibrium, the system shifts to relieve that stress. Now, applying stress to a chemical reaction might seem kind of strange to you because we don't usually think about stressing a reaction. So we're going to look at ways that you can stress a reaction and then what happens. And we'll look at the ways to stress it. There are really 4 ways. And then we're going to do some examples that explain what happens when that stress is applied. Okay, so there are 4 stresses. The first stress is if you change the amount of a reactant or a product. So the way that you can do that is by either adding more of a reactant or product or removing a reactant or product. So if you add a reactant or product, the reaction wants to get rid of it. So it's going to shift toward the other side. So if you add a reactant, it's going to shift toward the products. If you add a product, it's going to shift toward the reactants. So it wants to get rid of whatever you've added by shifting toward the other side. If you remove a reactant or product, the opposite takes place. The reaction wants to try to make more of it, so it's going to shift toward that side. So if you add a reactant, it's going to shift toward the reactants. If you add a product, if you remove a reactant, it's going to shift toward the reactants. If you remove a product, it's going to shift toward the products. So if you add something, it shifts away from that. If you remove something, it shifts toward it. And that's really the same principle that we apply to the next stress, which would be changing the temperature. And when you change the temperature, that means that we're going to look at whether the reaction is endo or exothermic, meaning is heat taken in an endothermic reaction, or is heat given off in an exothermic reaction. And you view heat as a reactant or product, and then you look at the rule above. So again, if you add something, it shifts to the other side. If you remove something, it shifts to the same side, whatever you removed was on. And we're going to do a lot of examples. The next stress, it would be changing the pressure. And this only applies to systems that are made up of gases. So if you increase the pressure, the reaction wants to remove that pressure, so it's going to go toward the side with the fewest gas molecules. So then if you decrease the pressure, it'll go toward the side with the most gas molecules. And we're going to do examples of all of these. I just wanted to go over the rules first. The other way you could stress a system, and I don't know if it's really considered a stress, is that you can add a catalyst. Now the catalyst, it changes the rate of the reaction, but it has no effect on the equilibrium because it increases the rate in both directions. So when you add a catalyst, it's going to increase the rate in both directions. So what you should do is go back, make sure you write down what we've just gone over, because now we're going to go through the examples and look at how adding or taking something away affects the equilibrium. And we're going to look at 2 examples. Okay, so the following reaction is endothermic. So what does that tell us about heat? Well, the fact that it's endothermic means that the reaction takes in energy as heat. Delta H is positive. Delta H is negative in an endothermic reaction, and heat is considered a reactant. Okay, so we're going to add heat to this side, except I'm not very good at doing it that way, so I'm going to type it in. Because it'll be easier to do that way. All right, so I'm going to add heat. So I'll go right here, plus, heat. All right, so it's an endothermic reaction, so we said heat is a reactant. And so we've added heat as a reactant. All right, so let's go back to the slideshow. So now we want to know whether or not the equilibrium will shift to the left or to the right. So if you remove some O3, O3 is a product. Again, if you remove something, it goes toward whatever side that substance is on. So this is the left side of the equation. This is the right side of the equation. The products are on the right, the reactants are on the left. So if we remove some O3, O3 is on the right side, so the reaction is going to shift to the right. Because again, if you remove something, the reaction shifts toward that side. It wants to make more of it. So if we remove some O2, here's O2. O2 is on the left-hand side of the equation, so the reaction is going to shift left. If you add some O3, if you add something, it shifts toward the opposite side. It wants to get rid of it. So you add some O3, it's going to shift to the left because it wants to get rid of it. Now, decreasing the temperature, again, we said heat was a reactant. So decreasing the temperature would be like removing heat. If you remove something, it shifts toward whatever side that substance is on. So it's going to shift to the left. Adding a catalyst has no effect. And then increasing the pressure will make it shift toward the side with the fewest gas particles. So let's look at the number of gas particles. There are 3 gas particles on the left, and there are 2 gas particles on the right. So the fewest number is on the right, so it's going to shift to the right. And again, in lab, I do examples. I was actually able to go into the lab and film, and I do a lot of examples of Le Chatelier's principle. The entire lab was on looking at actual chemical reactions that have color changes depending on what direction they shift. But all you really have to remember is that if you add something, it goes to the opposite side. If you remove something, it shifts toward the same side. All right, so let's go through and look at the last in-class exercise. And this is in-class exercise number 6. Okay, so in this equation, heat is already written as a product, right? It says that it gives off 327 kilojoules of heat. This is an exothermic reaction. So again, this is the left-hand side of the equation, and this is the right-hand side of the equation. Right. So if we remove some HI, HI is on the right. If you remove something, it shifts toward that side. So it's going to shift to the right. If you add some I2, I2 is on the left. You add something, it shifts to the opposite side. So it's going to shift to the right. If you remove some I2, it shifts to whatever side I2 is on, which is the left. Now, if you increase the temperature, it's like temperature is like a product. So it's like adding heat. Where, again, if you add something, it shifts to the opposite side. Heat is on the right-hand side, so it's going to shift to the left. Okay, again, adding a catalyst, no effect. And then if you decrease the pressure, it's going to go toward the side with the most gas particles, the opposite effect of increasing the pressure. But in this particular reaction, we have 1 + 1 or 2 moles of gas on one side, and we have 2 moles of gas on the other side. So increasing the pressure is going to have no effect because you have equal number of particles on both sides. Okay, so this is the end of the kinetics and equilibrium, or reaction rates and equilibrium unit. You should now be ready to take the reaction rates and equilibrium quiz.